Episode 6. Temporal Difference Learning. You're driving to a city 5 hours away. After 30 minutes of traffic, your GPS updates 5.5 hours. Traffic clears and it drops to 5.2. You don't wait until you arrive to learn how long the trip takes. You update after every segment. Now imagine an RL agent doing the same thing. In the last episode, Monte Carlo methods waited for complete episodes before updating values. Dynamic programming needed the full model. But what if you could update after every single step, using only what you've experienced so far? That's temporal difference learning. It combines the best of both worlds, the bootstrapping of dynamic programming with the model-free sampling of Monte Carlo. And it's the idea that changed everything in reinforcement learning. Let's place TD learning in context. In Episode 4, dynamic programming computed exact values by sweeping through every state. It bootstrapped. It updated V of S using estimates of V of S prime. But it needed the complete model, every transition probability, and reward. In Episode 5, Monte Carlo methods threw away the model requirement. They learned purely from experience, sampling complete episodes and averaging the returns. But they had to wait for each episode to finish. Here's the gap. Can we bootstrap, updating estimates from other estimates without needing a model? Can we update after every step instead of waiting for the episode to end? The answer is yes. And that answer is temporal difference learning. The core of TD learning is a beautifully simple update rule. After taking one step from state S, observing reward R, and arriving at state S prime, we update V of S gets V of S plus alpha times the quantity R plus gamma V of S prime minus V of S. Let's break this apart. The target is R plus gamma V of S prime. That's the immediate reward plus the discounted estimate of the next state's value. The prediction is V of S, our current estimate. The difference between target and prediction is the TD error, delta. This is bootstrapping. We're updating one estimate using another estimate. V of S prime is itself a guess. We're updating a guess with a guess. This might sound circular, but it converges, and it converges fast. Compare this to Monte Carlo. MC uses the actual return GT as its target. GT is a fact, the real sum of discounted rewards from that point to the end. TD uses R plus gamma V of S prime, which is available after just one step. MC must wait for the episode to end. TD updates immediately. Now let's see this in action on a simple problem. The random walk has 5 states, A through E, arranged in a line. At each step, the agent moves left or right with equal probability. Moving left off state A gives reward 0 and terminates. Moving right off state E gives reward 1 and terminates. All other transitions give 0 reward. The true values under this random policy are 1/6, 2/6, 3/6, 4/6, and 5/6. Starting with all values at point 5, TD updates after every single step. After 10 episodes, the estimates are rough, but trending correctly. After 100 episodes, they've nearly converged to the true values. The agent learns from every transition, not just from completed episodes. Now we can see the full picture. Dynamic programming, Monte Carlo, and temporal difference learning differ along 2 dimensions. The first dimension is bootstrapping. Does the method update estimates using other estimates? DP and TD both say yes. Monte Carlo says no, it uses actual returns. The second dimension is sampling. Does the method learn from sampled experience? MC and TD both say yes. DP says no, it computes expectations over all possible transitions. This gives us a 2x2 grid. DP bootstraps but doesn't sample. MC samples but doesn't bootstrap. TD does both. It bootstraps and samples. That intersection is what makes TD so powerful. Now, the bias-variance trade-off. Monte Carlo's target, GT, is unbiased. It's the real return. But it has high variance because it sums many random rewards over the entire episode. TD's target, R plus gamma V of S prime, has lower variance because it depends on just one transition. But it's biased because V of S prime is an estimate that might be wrong. In practice, lower variance wins. TD typically converges faster than MC, especially in the early stages of learning. The bias shrinks as the value estimates improve. On the random walk, TD reaches good estimates in tens of episodes. Monte Carlo needs hundreds. The choice between TD and MC isn't binary. There's a smooth spectrum between them, controlled by a parameter n. One-step TD, which we've been discussing, uses one real reward plus a bootstrap. G1 equals R plus gamma V of S prime. Two-step returns use two real rewards plus a bootstrap. G2 equals R1 plus gamma R2 plus gamma squared V of S 2 steps ahead. Keep going. N-step returns use n real rewards before bootstrapping. The general formula, Gn equals the sum from k equals 0 to n minus 1 of gamma to the k times RT plus k plus 1 plus gamma to the n times V of St plus n. At the extreme, when n equals infinity, you wait for the episode to end and use all real rewards. That's Monte Carlo. So TD and MC are endpoints on a spectrum, with n-step methods filling the middle. As n increases, bias decreases because you're using more actual rewards and less bootstrapping. But variance increases because you're summing more random variables. The optimal n depends on the problem. One of the most elegant results in RL connects TD and MC directly. The Monte Carlo return minus V of S equals the sum of discounted TD errors along the trajectory. MC and TD are deeply linked. Let's return to our 4x4 grid world from episodes 4 and 5. Same environment. The agent starts anywhere, moves up, down, left or right, receives -1 per step, and terminates at the top left corner. But now we compare two learners. The Monte Carlo agent waits until each episode ends, then updates V for every state visited. The TD agent updates V after every single step. Watch the TD agent in action. It starts at row 3, column 3, moves left, receives -1, and immediately updates V of 3.3 using the bootstrap V of 3.2. Moves left again, updates V of 3.2. Every step teaches something. After 10 episodes, both agents have rough estimates. But look carefully. The TD estimates are smoother, more consistent. They spread information faster because each step updates propagate backward through the chain of visited states. After 100 episodes, both converge to values close to optimal. But TD got there with less total experience. MC needed full episodes. TD needed only steps. On this grid, TD reaches a good policy in about a third of the episodes that MC requires. Here's the deeper story. In 1997, neuroscientists Schultz, Diane, and Montague discovered something remarkable. Dopamine neurons in the primate brain fire in a pattern that matches the TD error almost exactly. When a monkey receives an unexpected reward, dopamine neurons burst. That's a positive TD error. Reality exceeded the prediction. When a reward is fully expected, the neurons are silent. Zero TD error, prediction matched reality. And when an expected reward is omitted, the neurons dip below baseline. Negative TD error. Reality fell short. The brain bootstraps. It doesn't wait for final outcomes. It updates predictions from predictions, moment by moment, exactly like TD learning. The TD error is, quite literally, the brain's surprise signal. This isn't a coincidence. TD learning is the computational foundation of nearly every major algorithm in modern deep reinforcement learning. DQN, the algorithm that learned to play Atari games from raw pixels, minimizes the squared TD error. PPO, the algorithm behind ChatGPT's fine-tuning, uses TD errors to estimate advantages. SAC, the leading algorithm for robotic control, extends TD with entropy bonuses. They all trace back to the update rule we learned today. Rich Sutton, who invented TD learning in 1988, has called it the single most important idea in reinforcement learning. After this episode, you can see why. Let's lock in what we've learned. First, TD prediction updates values after every step using V of S gets V of S plus alpha times the TD error. It bootstraps from value estimates, no model needed. Second, the TD error, delta, measures surprise. Positive means better than expected. Negative means worse. 0 means the prediction was perfect. Third, TD sits at the intersection of DP and MC. It bootstraps like DP and samples like MC. Lower variance than MC, biased but fast converging. Fourth, end-step returns interpolate between TD and MC. More steps means less bias but more variance. The optimal balance depends on the problem. In the next episode, we go from prediction to control. TD tells us how good states are, but we need to know how good actions are. SASA and Q learning turn TD into a decision maker, and a simple cliff-walking problem will reveal a profound difference between learning safely and learning optimally. See you in episode 7.